Yeah, hello, good morning, everyone. Thank you so much for coming in person to ICTS. It's wonderful to be back, with all our friends after many years. As you know, I mean, this program that we have is structured into sort of broadly two parts, not very firmly.
Sí.
In the first week, we would have a series of pedagogical lectures before lunch, and followed by sometimes lectures, but sometimes also a little more focused talks, in the afternoons. Whereas in the second week, we'll mostly be focusing on, let's say, a conference workshop type sort of special focus talks on the state of the art in the field. So I think a combination of these will allow the young PhD students, the postdocs, to sort of also, not only come with terms with what is going on in the field in the recent past, but also to get a pedagogical understanding of the diverse different parts of this vast domain of frustrated metals and insulators that is progressing at a very fast pace. And we've specially requested all the speakers who are giving these school lectures to be sort of very elementary, so that people who are not working on that domain can more logically follow the construction of all the basic ideas and the consequences that follow in these the other topics. So with this, let me first sort of welcome Professor Karlo Penc from Wigner Research Center in Budapest, Hungary, who will begin and sort of give the first set of lectures on microscopic Hamiltonians and how to derive them from fundamental considerations of symmetry, for which are of broad application in understanding both the materials as well as the current theoretical understanding of frustrated metals and insulators. So let's welcome Karlo Penc. Yeah.
One, two?
Yeah, yes.
Okay, I think it works. Very good.
Yep. There's a presentation. There's a presentation.
You mean for the laptop? Yeah. We can do it maybe in the break, because the first our only blackboard and later. Yes, I will show you example. Thank you very much. Yes, great. And as I mentioned, particularly Yasir and Subhro for really taking care of people coming here and facing different aspects of Indian life. Excellent. So I will talk, perhaps you will find my lecture boring. I'm sorry for that, but this will be something that we need to go through. This is the basics, the basic ingredient of what we are later studying. The question is how the interactions arise between the magnetic degrees of freedom in materials. So we have very boring materials in the magnetic or electronic sense. Like, for example, this desk is not conducting electricity. This plastic thing is also not conducting electricity. It's just very boring, trivial. And the reason for that is that we know that all materials consist of atoms and molecules and so on. And in all those things here, we have a closed shell of electrons. They are somehow, to create some excitation, we need to invest a lot of energy. So these are, if you wish, these are Slater insulators in a more physical word. What we are interested in, and mostly me and some of you, is the Mott or charge transfer insulators. The charge transfer insulators means that they don't conduct electricity, but at the same time, there are some internal degrees of freedom which may interact among each other. And this interaction will give rise to many, many interesting phenomena that we didn't even dream of like 10 or 20 or 50 years ago. So let's start. Subhro told me that there will be, I asked, is there a blackboard? He said, yes, there's a linear blackboard. Fine. I didn't get what he means, but now I see this huge linear blackboard. This is great, because I'm not sure if I will be able to fill it. I think when he said that I won't be able to fill it, I thought, oh, he's joking. But I think I won't be able to finish it, to fill it all. But I have a serious question. If I write here, will you able to see it at the back? So I will start, and if you can't, then you'll say, please write bigger. Okay, and I will try to write bigger. Maybe I start somewhere here. Yes, because this is long enough. And I started my career in 1D physics. So this should help.
We can start.
Okay, very good. Yes, perfect. Right. Okay, so insulators. So the question is, okay, may I assume that the spin algebra is familiar to all of us, all of you? You know, spin 1/2, how you deal with spin 1/2, the commutation relation, and so on. If not, then you may ask questions, or I don't know. And really, please ask questions. Interrupt me anytime. It's important. I have a list of what I want to talk. I'm not sure if I can go through everything, but I have a plan B and a plan C if I don't get there. Okay, so the question is that, okay, so usually what we have this, say, a crystalline solid or whatever, and there are different atoms. For example, we have these 2 atoms, and there are some degrees of freedom that are like magnetic ions. These are magnetic ions, and they are like spins. This magnetic ion originates both from the orbital part of the L of the moment of the electrons and the spin itself. Now, there is an interaction between those 2 guys. The question is, what is the interaction? What different interactions we can have, and how large it is? What is the sign of it? Is it ferromagnetic or antiferromagnetic? So if you followed electrodynamics course or just static magnetism, then you know that if we have 2 magnetic moments, they will interact with the dipole-dipole interaction. And the dipole-dipole interaction is something, I will call this a mu1, and I will call this a mu2. And is it visible? Ludo, can you? Good, okay, very good. So then the dipole-dipole interaction goes as follows. It is the mu1, sorry, I usually underline the vectors, but is it fine if I leave it underlined, or you would like me that I draw the arrows on top of the? It's fine, okay, yes, good. So it is mu1 dot mu2, mu2, yes, divided by r to the cube, minus 3 times, and here's the unit vector pointing in the direction of r, mu1 times the unit vector pointing between, this r is just the distance between the 2 guys, I mean the vector, and here's the mu2. Perfect. So this is the interaction between 2 magnetic ions. If you put numbers in, you know now probably you know all those very strong rare earth magnets. It's a neodymium something. I forgot the precise composition. They are made of rare earth elements that have F electrons. F electrons have the largest magnetic moments of the atoms. In that case, and if you take into account the distance between them, in that case, for F electrons, the largest moments you can think of, and they are very close to each other, this energy is about 2 Kelvin, about 1 Kelvin. This is okay. For example, there are some materials that are called holmium, titanium 207. These are the so-called spinized materials, or dysprosium 2, titanium 207. In this case, is the interaction coming from the dipole atom is about 2.3 Kelvin. It's very tiny, very small. In everyday life, we observe exchanges. Okay, everyday life, I mean physicists, not in the kitchen. So we see energies that are like 1,000 times larger. The effect interaction between the magnetic ions is about 1,000 Kelvin. So how do they arise if not by this dipole-dipole interaction? So let's try to look at the simplest model of Mott insulators, and that is the Hubbard model. Right. So what is the Hubbard model? We have two sides, and we have some orbitals on these two sides. It can be s orbitals, or p orbitals, or d orbitals, whatever you wish. And there's only single orbital per side. And then we can put either nothing or one electron. The electrons have spin 1/2, and they can point, say, up or down. So we can point a single electron, or we can put 2 electrons. If we put 2 electrons, then there will be the electrostatic interaction between them, and this will cost energy. So the Hamiltonian, or the Hubbard model, is the following. I will write, okay, and there is a small overlap between these two orbitals, so maybe I should, you know, I mean, they extend. There is some, let me use the colors. So this is one orbital, and then this is the other orbital. And there is a small overlap, and you can, and because of this small overlap, there will be a possibility for one electron on this side to jump over to the other side and vice versa. So to describe this process, we introduce minus t times, and then here I write C up, C1 sigma, dagger C2 sigma, plus C dagger 2 sigma, C1 sigma, plus the energy of interaction, which is N1 up and 1 down, plus N2 up, N2 down. Can you still see this? I can't be, I need to see you if you can see. Is it okay still, the size of the letters? Not so. Okay, Ludo is saying that I need to draw it. Okay, so, right, so this part here, yes? Not smaller than that. Okay, fine, thank you. Yes. So this term here, U, is taking care of the electrostatic repulsion between the electrons. So if there are 2 electrons on one of the orbitals, it will cost you energy U. U is very large, it's about 10 electron volts typically. It depends on the type of the orbital and so on. The T, this is the hopping amplitude. This is the probability or amplitude that electron hops from one side to the another one, and this is also in the electron volt range. Harald is here. Harald is doing ab initio calculations, and probably if you are really interested in the numbers here, I think he's the right person to ask. Right. So what are the states? So we can have, I will use E for empty side. I will use sigma for a site occupied by a sigma spin electron, which can be pointing up or down. You see, I used here up arrow and down arrow. And I will use D for a doubly occupied site, which means that the 2 electrons are present. The sigma, okay, so empty, this is just nothing. The sigma is that I take the empty side and I apply the C dagger sigma operator on this empty side. And the double is I apply the C dagger up, C dagger down on the empty side. And this C these are fermionic operators, and they anti-commute. Because of that, it's important to know the order of these operators. And what we will use in the following, there are different possibilities, there are different conventions. I will side order them. We can use different, you may first choose to write the spins, up spin operators and then down spin operators. So these are my states. Is this fine with you? Any questions so far? Okay, very good. Now, what can happen? So let's try to apply the Hamiltonian, the state which I write like sigma empty. It means that we have a sigma electron on this side, and this second side is empty. So this is number 1, this is number 2. So what we do is that we apply, and this we, the Hamiltonian, the U, it requires 2 electrons. There is only 1, so it will not act. Only the T will act. And this is on side 1. So what will happen is that this one will eat an electron on side 1, and this will create it at side 2. So this matrix element will be minus T times C dagger 2 sigma, C1 sigma, applied to the C dagger 1. Okay, this is sigma prime, there's a sum here, and to the empty. Okay, and this guy will give, we can apply the anti-commutation relations for the fermions. This will be delta sigma prime sigma minus C dagger 1 sigma C1 sigma bar. So this is what turns out when we apply the anti-commutation relations. And this will be acting on the empty vacuum. I will put here 2 E's. So this is this here. And there's a C dagger 2 sigma prime, sum over sigma prime minus T times. This thing here, if acting on vacuum, will give 0. It will cancel out. So it means that the sigma and sigma prime needs to be the same. This is this term that is acting. And we will create a sigma electron on side 2. So this will be minus T times empty sigma. Okay. We can apply the same Hamiltonian to this guy, and then we will get that it will be minus T times sigma E. So we can write up a 2 by 2 matrix. So the basis is, and we don't leave this basis, it's empty sigma and sigma empty, and the Hamiltonian is just 0, minus T, 0 in this basis. Is this fine? Does this mean not so? I started to learn what this means, but okay, yes. Because that will be on the next board. It will come, right? Okay, so this is, we have no double interaction, no double occupancy. We don't have this 4 fermionic term. There is no interaction. So this is the non-interacting part. We can easily solve this. This is trivial. We will get 2 eigenvalues. We will get energies that are plus and minus T, and the corresponding eigenvectors are 1, 1 for the plus, and for the minus, 1, minus 1. Maybe I write it like this. Minus T energy equal plus T. And the corresponding wave function is empty sigma plus sigma E, and this is empty sigma minus sigma E. Okay, so this is that we see that we have a parity plus and parity minus solution for the single electron. Now, Niels wants to know what happens if we have 2 electrons. So per orbital, so the U part is not acting. Can they hop? Well, they will be happy to hop, but this is already up, and it cannot hop because the other side is already up. So the energy, if we apply the Hamiltonian to this guy, it will give 0. It will do nothing. So this guy has energy 0. Similarly, we can apply, and the same holds for the down-down. Okay, good. Let's go further. We can have a situation where we have up and down. In this case, the up can hop to the side 2, or the down can hop to the side 1. And then there will be something going on. Let's try to work this out. So this is up-down. It is like C dagger 1 up, C2 dagger down, acting on an empty on the vacuum. Then we need to have the down up. And then here, when I said that there is a convention, here it comes into play, because you may write, like you may say that, okay, so let's write the upspin operators first. Or you can say, I mean, that would be like, and please don't write this in your notebook because I will erase it. So you could do it like C2 up, dagger C1 down, empty. So this would be convention when you say that all the upspins are going first. Or we can use another one, and that is that instead of this, I will write C1 down and C2 up. Here, what I'm doing is I'm putting first the operators that are increasing in size. And these two conventions will produce a minus sign with relative to each other. To be consistent, it doesn't matter which one you choose, but you need to be consistent, and I'm choosing this one. Now we have the empty double, and there it is like C dagger 2 up, C dagger 2 down, empty, and we have the double empty, and that is C dagger 1 up, C dagger 2 up, 2 down, C dagger 1 down, acting on the empty. So this is the local Hilbert space, and we start to act the Hamiltonian onto this state. So let's do it. Hamiltonian acting on empty. How much do I spend with time? Okay. I
5 minutes now. You have gone like
25 minutes. Okay. H applied to the ED what will it give us? So it is H applied to the C dagger 2 up, C dagger 2 down, empty, and it will be minus T times C1 dagger sigma, C2 sigma, plus C dagger 2 sigma, C1 sigma, applied to C dagger 2 up, C dagger 2 down, empty, plus, I will continue here, U times M1 up, M1 down, plus N2 up, N2 down, apply to the C dagger 2 up, C dagger 2 down, empty, empty. Good. So this is how the Hamiltonian acts. Now, here we will have 2 electrons on side 2. So this will be acting this knot, and it will give us a U. Here, we will transfer electrons from orbital 2 to orbital 1. So this is not acting, and only this one is acting. First, it will act with the upspin, and then it will act with the downspin. Now, if we do this, let's write it out. It is minus t times, so C dagger 1 up, C2 up, C2 down, up, acting on this guy, C2 up, C2 down, dagger. I write EE at the, okay, I write EE like this. Then with the downspins, C dagger 1 down, C2 down, C2 up, C dagger 2 down, empty, empty, plus U times, this is diagonal U times empty double. Okay. Here I can do the the commutation, and essentially this will eat each other, and what will remain is that I will move the upspin from side 2 to side 1 minus t times, maybe I do it slowly, C dagger 1 up, C2 down dagger, empty, empty, it's fine, plus here, this is the annihilation operator of downspin, and the other one is here. There is another family operator in between them. So if I move this C annihilation operator next to the creation operator, I will cross the C dagger, and it will give us a minus sign. So I need to change this plus to minus. And I shall write C dagger 1 down, C dagger 2 up, acting on empty, empty, plus U times empty double. Happy? Good. So it will be minus t times up, down, plus t times down, up, plus U times empty double. Okay. So we can write the first column in our 4x4 Hamiltonian. That looks like follows. So this is a Hamiltonian in the 4x4 basis. It will be U, and my elements, but I use the convention that the basis is empty double, then it is up, down, down, up. This is the Hilbert space, double, empty. Right. So there will be a minus t, there is a t, and there is 0. So this is the first column. Now, we can continue, and then if we continue, we will end up with the followings: 0, 0, minus t, then t, 0, 0, t, and 0, minus t, t, u. So this is the 4x4 matrix that we need to solve. Okay? Good. Subhro, look, I almost filled the blackboard. Yes. Okay, so is this a hard wall?
No, it's the Berlin wall. You can make it.
What? Okay, camera cannot follow me anymore. Okay, so let's go there. Yeah. Okay. Very unfortunate. Yeah. Okay, so okay, I will copy this matrix there. So U minus T0 minus T0 0 minus T and minus T. Okay, this is the matrix. So let's try to find the eigenvectors. We can. It's clear that if we choose 0, 1, 0, 0, minus 1, that this is an eigenvector, right? Because if you act with it, this will give U, this will be 0, 0, minus U, so the energy of this guy will be U. And this is empty double minus double empty. Okay, good. Similarly, I can use 0, 1, 1, 0. This is another eigenvector. It will also have it will have energy equals 0, because it will, if we multiply this vector with the matrix, it will give 0 here, because it will minus T plus T is 0, here nothing, and again nothing, so we will get everything 0, so this is eigenvector with eigenvalue 0, and the corresponding states are up, down, plus, down, up. Very good, and let's stop here for the moment. Here, already we had some guys that have 0 energy. The up, and down, they have 0 energy. And we found a third one that also has 0 energy. This guy here. So there are 3 states that have 0 energy. This guy, and that guy. So up, down, and up, down, plus down, up, they all have 0 energy. And these are nothing else but the spin, the total spin of these two spin 1/2 of this state is spin 1. You apply the SZ for these two sides, and then you will get 1/2 plus 1/2 is 1. And they really belong to the S equal 1, the triplet representation of two spin 1/2. Is this fine with you, please? If somebody, I can explain it in more detail if needed. Okay, nobody is saying no. So they make a triplet, spin S equal 1 triplet. Very good. Now, this is some other guy. And then there are still 2 eigenstates that we need to take care of. They're a little bit more complicated. And I need to delete starting point. The eigenvectors are not normalized. U plus minus U square plus 16 T square minus U minus plus U square plus 16 T square and 4T. The corresponding energy is U over 2 minus plus square root u square over 4 plus 4t square. This is a little bit more complicated. Let's try to draw the energy levels of this problem. This is the single particle. In the single particle, we found two states. One is having energy minus T, and the other is having energy plus T. So if there is no interaction, we will have these two energy levels. I think I will just come here. So here we have the energies, and here we have the U over T. So this is strong interaction. Here it is 0. It is no interaction at all. And for the non-interacting case, we can use the single particle picture. We have two orbitals. The two orbitals are the minus T1 and the plus T1. Now, we can put two electrons on the lower one, on the bonding one, and this will be energy minus 2T. And I don't want to, let's see, I have a red color. I have a, yeah, very good. I have colors, this I will use. So, here I have minus 2T, and this will correspond to filling these two orbitals. Maybe I was not, let's do it. Let's do it differently. So there is a plus T, minus T level, and we put up-down electrons to the lower one. It will be the 2T, minus 2T energy. Then we can put the up spin, down spin on the two, on the anti-bonding and bonding orbital. In that case, the energy would be 0. Or we can put both electrons onto the anti-bonding orbital, like this here. In that case, the energy will be 2T. This is only one possibility to do this. So this is one-fold degenerate. Here, it is also one-fold degenerate. We can do it only one possible way. And here, we put the up and down. We can choose whether we put the down here, up there, or maybe we put down here, and so on. So altogether, there will be 4 states at 0 energy. Right, 4 times degenerate. Okay, these guys here are singlets. So here, I mean, because we have an up, down, they if we apply the spin raising operator to this animal here, we get 0. So this is definitely a spin 0 object. This is also a spin 0 object. So these two are singlets. And here we can have an S equals 0 or S equals 1. S equals 1 will be something that we encountered here, this up, down, plus down, up, and I think, yeah, and then these guys. Okay, so this is what we learned from the non-interacting case. Now let's draw what happened for finite U. The triplet continued to have 0 energy. So the triplet continued to have 0 energy. These are these guys here. Then we had a state that I think I deleted, that was empty double nodes here, where the empty double minus double empty is just having energy U. It is because that the interference, that if we want to split the double, it will produce a double up, down, down, up, just the opposite sign with this guy. So So the delocalization doesn't play a role here. So energy is equal to U, and that I will use a different color. Maybe I will use the blue. And the blue is going up linearly proportional to U. So this is the empty double minus double empty. Okay. Here we have the up, 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 down, minus down, up, and the down, down. Okay. And then what remains are the. Thank you. Yes. And what remains is this energy here. If we draw it, you can use your favorite plotting program. It is something like this and something like that. Right. It will approach from below this energy zero. So let's look at this one. So this energy is, we need to use the minus sign. So this is U half minus square root U half squared plus 4t squared. This is the energy of this guy. So because here we have U half, and we have the same thing squared plus some quantity, positive quantity. So this will be larger than U half, so this will be negative. This will be always below. We can expand this in for large U, and then this will become minus 4t squared over U. So there is an energy difference between this yellow level, that is a singlet, and this upper level, that's E equals 0 level, that is a triplet. So what we get a splitting between the singlet state and the triplet state, which has energy minus 4t squared over U. And in fact, this is the origin of the exchange interactions in Mott insulators. Right, so let's try to be more specific, but before that, let me also try to write you the wave function in the large U limit. It will be up, down, minus down, up, and plus 2t over U. I'm expanding the wave function that is over there. That's 2t over U times empty double minus double empty. Is it right? Maybe plus? I think I need to write here plus. Sorry. Okay, so what it tells me that it is not pure, the wave function is not only composed of a single occupied size, but there is a mixture of charge fluctuating part. So there will be always some double occupied sites in this wave function. And this is very important. So if you have a Mott insulator and you apply some probe that is interacting with the charge densities, you will be able to see this part. And you will see signature of these charge fluctuations in your dynamical spectra that you are measuring, like EELs, this is electron energy loss spectroscopy. To take into account these parts is important. So what do we learn here? Okay, so let's first, let's try the effective Hamiltonian, and then we will discuss what happens. So how to write the effective Hamiltonian? So we have two spins. This is a triplet, this is a singlet, and the singlet is lower in energy. So I can write the H effective equal to 2t squared over U times S squared total minus 2. The S total for the singlet is 0. So this will give me minus 4t squared, which is this energy. Okay? Right. If we act, what is the S total square of the up, say, the triplet, it will be equal, this is a spin 1, so it is S times S plus 1, it is 2 times up. So this is spin algebra that I hope you know. So in that case, if we apply this Hamiltonian to the up, we will get a 2 minus 2 is 0. So this effect, each effective applied to the up will give 0. Let's expand this. Is it fine? You get the idea? Please nod if you don't. Okay, so what I want to do, right, so what we know, what we learned so far is that here we have spin eigenstates of the total spin, and they are spin triplets. This guy here is essentially a spin singlet, S equals 0. So they are both eigenstates of the total spin operator. So the S total operator is just defined, I mean, like alpha component of the S total is just sum over alpha, S1 alpha plus S2 alpha. So this is the total spin operator. And it knows everything what it shall know about the SU2 algebra of the spins. And if we apply, for example, SZ total to the up, it will give us 1/2 plus 1/2 is 1 times up. So the SZ total of the up is just 1. If we apply the SZ total to the up-down plus down-up, it will give us plus 1/2 minus 1/2 gives 0. So this gives 0. So this is the SZ equals 0 part of the, we don't know if it is a triplet or not, but if we apply the S plus total to the up-down plus down-up, it will give us up with a coefficient that I am not pretty sure of. So there will be some coefficient here, the proper one. I haven't used here, I didn't normalize the states, blah, 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 so I'm not sure about the coefficient here, but nevertheless, we will be able to raise this SZ0 state into this state here. So it tells us that the up-down plus down-up, and the down-down, and the down-down, minus 1 times down-down, that they are part members of the S total equal 1, SZ equal 1. This is the up, S total equal 1, SZ equal 0 is the up-down plus down-up, and with the minus 1 here is the down-down. And we have the up-down minus down-up. If we apply the SZ operator to this guy here, it will be 0. And if we try to raise it, if we apply the S plus total up-down minus down-up to this guy, what will happen is that we try to to move the downspin to upspin, because that is the spin raising on side 2. It will be up, minus, I want to raise the downspin here. It will be also up, and the 2 will cancel. So I cannot raise this state anymore. And if I cannot raise it anymore, and the SZ is equal to 0, this guy must be a singlet. Is this fine? Or getting clearer? Okay, so what we know that these states are eigenvalues of the total spin operator. So if they are eigenvalues of the total spin operators, eigenstates, in that case, we can write the effective Hamiltonian, just that this total square that acts on these states, and it will produce as diagonal elements, and they will produce as the 0 and the minus 4t squared over u. So if we have this Hamiltonian and we act with this Hamiltonian to a triplet state, then the S square total acting on the up will just be 2 times up, because the S square, I mean, either you calculate it or you know that the S square of some spin, of some S spin will be S times S plus 1, the same S spin. So we use this fact, that if we apply the total square of a spin, total square of the spin operator to a triplet or singlet, we will multiply the state by S times S plus 1. This is coming from the spin algebra. So this is what I wrote here. Yes? Yes? It's charge fluctuation because if we can ask what is the expectation value of the charge in this wave function. The expectation value of the charge will be just 1. There is only one, I mean, on every side, altogether we have 2 charges per 2 sides. But if we ask what is the expectation value of the n square, and look at the fluctuation, n square expectation value minus expectation value squared, it will give a finite value, and it will be proportional to this d over u, d squared over u squared. Right. So, okay, so is this okay now? Yes. Yes, it is only for very good question, very good remark. This guy here is the effective Hamiltonian for these 2 levels here. Yeah, H effective. That's correct. We are only describing these 2 levels here. Yes, it will. It will. And there is also a t squared over u contribution here. And that is a different story. There is a larger algebra that can be associated with the Hubbard model. Right. Okay, so if this is the Hamiltonian, let's work on this a little bit further. So S squared minus 2. Where do I go? Let's just go here. So the H is 2t squared over u, S total square minus 2. This is the Hamiltonian. I expand this 2t squared over u, and here, this is like S1 plus S2. Okay, so these are operators squared, and this will be 2t squared over u, S1 squared here, plus 2 S1 dot S2 plus S2, I shall write bigger, S1 squared plus 2 times S1 dot S2 plus S2 squared minus 2. I'm just rewriting this full square. If we apply the S1 square to spin 1/2, then the S times S plus 1 for spin 1/2 will give 3/4. 1/2 times 3/2 is 3/4. So this here is equal to 3/4 plus 3/4. So this here is equal to 3/2, 3/4. We have 2 of them, that is 3/2 minus 1/2. It will be minus 1/4, minus 1/2. So this is equal to 2t squared over u, 2 S1 dot S2 minus 1/2. And here maybe this is okay, like this. So this is the effective interaction written using the spin operators on side 1 and side 2. So what we learn, and one can calculate what are these numbers here. We have electron volts and we have electron volts. So this can be very large. This can be electron volt, and 1 electron volt is 10,000 Kelvin. So from this process here, the fact that there is a Pauli principle and we cannot put two upspin electrons on a single side, but instead what happens is that we have this, the downspin, which makes a singlet, visiting the neighbor. Of course, it will pay some energy, but the ability to visit the neighbor and come back, that is what will give rise to the exchange interaction between the magnetic ions in a solid. You also see here that in the beginning, we had here the dipole-dipole interaction, which was something like S dot S, that was a isotropic part, and there was another term that was the R dot S times R dot S, and that is anisotropy. So that Hamiltonian, the dipole-dipole interaction is not isotropic, but this guy is. This is an isotropic exchange. So whenever we don't have something that is called spin-orbit coupling, that I was hoping and still hoping to be able to talk in the second lecture, the effective Hamiltonian is isotropic. It doesn't know about the details. I mean, the spin rotations and the real space rotations are yet decoupled, right? Okay, so do you have any questions now here? Okay, good. Yes. Sorry, I can't hear you acoustically. Just shout, please. Yes. Yes. There is one word that I don't understand. So here, what we do is that we put, there is a minus T level, and I can put up and down there.
Yeah,
Yes?
but then you are telling this is non-interacting case.
Yes, this is a non-interacting case, that's right.
So, but
Because
when,
U is equal to 0, I'm
oh,
here.
Okay.
Really here, this is the U over T. At U equals 0, they don't talk to each other. If you look at what is this wave function, you need to, yeah, there was this up, down, plus down, up. You need to check what is this, and if you expand this wave function, you will see that it will be like having components that you have a single electron, one electron on one side, another electron this side, and it will have equal probability of having two electrons on one side, right? And that will lose energy later. Yes.
So you have taken only 4 plus 4 levels.
I think he must. Okay, so here I had one state, here I had one state, and here I had 4. So
in metric form,
yes.
you have taken 4 cross 4.
Yeah. Because I was.
2 were 0.
Yeah. I neglected the up because yes. In this matrix, there are also the. I mean, if we take into account 6, there is another 0 here and 0 here. This is the up, down. Yeah, right. Okay, good. Yes. 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 Here I was talking. Yeah, this is just the effective model. And if you do expansion, very good. Thank you for this question. If you do the expansion in T square over U, T over U, only the nearest neighbor, those states, those sites will contribute that are connected by a single hopping. Further hoppings will contribute in higher order of expansion. And maybe I will be able to talk about how do I stand with time. It's very bad, isn't it?
It's like an hour.
Over.
Yes.
Oh, and 20 more minutes.
Yes.
Yeah. Okay, yes, good. Excellent. So this was kind of troublesome. We had the square roots and so on. Can we derive it differently? Let's try to get some physical picture. And let me erase this. Until here. So we can do perturbation expansion. Starting from U large limit. If U is large, then the low-lying states are the spin states, up, up, down, down, up, down, down, up. Let's see, suppose that we start from the up, down. What can happen? Well, what can happen is that we can hop this up electron to either side 1 or vice versa. Then there will be, and what this axis is here kind of the energy. So this is kind of 0, and this is kind of U. Okay? So we can hop with a probability minus d to the double empty. And this double empty can hop either back here or hop or exchange the two spins so that we get down, up. And this will be probability t. This is what we calculated, but you can get it differently. Similarly, there is a minus t probability that we go to empty double, and it will connect with t to these guys here. And we know that in perturbation theory, second order perturbation theory, the energies are given by, here we have like a ground state, Hamiltonian, excited state X, H, here again, ground state divided by energies, Ax minus A naught, okay? This is a little bit hand waving because what we are doing is the general perturbation theory. It's a little bit more involved mathematically, but essentially this is it. What we want to do is that we will have an effective matrix element that will connect this state, and the value of the effective matrix element is the transition probability, T, divided by the energy, U, and transition is 2 times, so it is T squared. And what we end up with is that that we can write something like this. There's an upspin, downspin, downspin, upspin, and there is a 2t squared over u probability coming from this expression here of the second order perturbation theory. Yeah, maybe there's a minus sign here. That will connect these two spins. If starting from up down, I hop to one of those, I can also come back. That will be, I will just draw it with this arrow, that this has some self energy that is minus 2t squared over u. And here, the same thing here, minus 2t squared over u. So these are the processes where these red arrows come from a second order perturbation theory from the fluctuation part. Okay? Excited, virtually visiting a double occupied site. Then we could write that this effective Hamiltonian is two t squared over u P12 minus 1. Okay, so now you see something new, this P12. What this P12 means is that it will just transpose or swap or permute the states that are on side I and side 1 and side 2. So this is just a permutation operator that will take, or exchange operator if you wish, that will change up down into down up here. And let's see how does this work. So in case that we apply it to the up down, we get down up minus up down, and those are those coefficients, that amplitudes that I have written here in the red. And this thing here is precisely the same thing what is written here. You can check, if you wish, the homework, that if you apply the S1 dot S2 times 2 to spin up down, and you subtract this minus 1/2, you will get precisely this operator here. This only works for spin 1/2. Okay, for spin 1 it does not work. Right. Niels had a question. What happens if the lattice is more complicated? What can happen in that case is that maybe we don't stop at the second order perturbation theory, but we do something else. Right. Suppose we have a triangular lattice. And we are not working with electrons, but we are working with helium-3. And these are the top layer of a helium-3 on a graphite lattice. The helium-3 electronic shell of the helium-3 is closed. Only the magnetic degrees of freedom are the nuclei. The nuclei have spin 1/2. What can happen in this case? What can happen is that, for example, we take an atom A and B, and somehow they move in real space and then somehow exchange themselves. But this costs a lot of energy. It's much easier to have like a ring exchange when this hops here, and then the other guy hops here and then hop here. You see that somehow there is a reconfiguration of these guys, and they just rotate around each other. Or maybe they can also take 4 spins, and they can rotate. This goes here, this goes here, this goes here, and this goes there. So these are so-called ring exchanges. Right. In that case, the effective Hamiltonian can be conveniently written using the Pij's and Pijk's and Pijkl, where, for example, this Pijkl means that this is Ijkl, that the spin hops from this side to this side, from here to here, from here to here, and back. Right. And these terms were important to understand the physical properties of helium-3 on a graphite. They will lead to spin liquid-like properties. It will not order. If we are dealing with spin 1/2, it turns out that this guy, if we look at the P1, 2, 3, and we also need to have the Hermitian conjugate, which is 1, 3, 2, that this does not exist in the sense that it will be decomposed into P1, 2 plus P1, 3 plus P2, 3, and there is a number here, maybe -1. Sorry, I am not. I think probably it's fine. So that if we act on the spin 1/2, then this will contribute to the 2-side exchanges. So the effective Hamiltonian will be 2 sides and 4 side exchanges and 6 sides and so on. But the 5 sides, 6 sides, and so on. Another example is the lanthanum copper oxide. Maybe I delete this here. Yes.
So it's not, I mean, so the spin is the Subhro spin. So I mean, it's the occupancy of the helium itself that
Yes, 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 but the spin goes with it.
That's right, but it's not the exchange of the spin of the medium in the nucleus.
What is the difference? I mean, your atom is characterized by the spin that is inside. I agree, distinction shall be made, but essentially we end up with the same thing. But Yogesh is right, we are exchanging atoms. It's different from what we did here because the atomic orbitals were staying on side. 1 ton copper oxide, and I need to put some numbers here, and I hope I will get them correctly. Okay, line 2. Now, can one help? What? Okay, okay, 2, 4. Yes, 2, 4. Good, excellent. This is a square lattice of copper d orbitals and the oxygens, and like this. Maybe I use green for oxygens. And what happens in this material is more complicated. We will have something that is called super exchange, and we will have something also that the ring exchange part will come into role. So far, we discussed the Hubbard model. Hubbard model, 2 sides, and there is a direct exchange. There is a hopping from one side to the other side. But in the London copper oxide, the spins are sitting on the d orbitals of the copper. Here are the spins. And there is in between the oxygen d orbital. So if we are to draw a perturbation expansion, in this case, it would be more complicated. How will it look like? So what we start with is, okay, so this is not precisely in a more strict sense, this is not a Mott insulator, this is a charge transfer insulator. What does it mean? Certainly, there is a U for 2 electrons on a single copper side, but there is a smaller gap when the electron hops from the copper to the oxygen level. Then the energy will be the difference between the chemical potential of the copper d and the oxygen p orbital, and that is the so-called charge transfer gap. Let's see what happens in this case.
Karlo,
Yes.
I have a question. So what is the lowest energy experiment that can tell the difference between a Mott insulator and the
APES, or then,
APES.
yeah,
I see.
APES, you will see very clearly, I think Zawadzki group, they were working a lot trying to figure out precisely what's going on, how it goes, and so on. Yes, or some experiments like electron energy loss spectroscopy.
But as far as the spin physics is concerned, I can...
You are ignorant. Essentially, you are ignorant.
Okay.
Whether it's coming from charge transfer or whatever.
Okay.
Yeah.
Thanks.
What did I do wrong? 214. Thank you, Howard. Yes, yes. I knew that something is fishy. Yes, that was a question.
How do you distinguish, like, what is the difference between Mott insulator is when you turn on this interaction? Because of the interaction, it goes into insulator.
Yes, so perhaps I shouldn't have mentioned this because it is just it depends how you deeply want to dig into the properties of materials. But I mean that the difference is that you look at we can look at the energy spectrum of this guy here, forgetting the spins. And then what will happen is that you have the lowest state is where the electrons are all sitting on the copper. Then what can happen is that there are also other states where, for example, electrons sitting here. I'm looking at the diagonal part, no hopping, nothing. You can put electrons here, a single particle picture like yeah, right, no hopping. Then you can put one electron here on the p orbital, and then what you will see that there will be, okay, so this is, okay, the ground state is that all electrons are sitting on the copper. Okay, let's do it this way. Yes, very good. So this is the, I just write, yeah, just two coppers and an oxygen. Right here. So if there is a one spin and let's call this like sigma empty sigma, and the middle one is the oxygen, okay? So this will have energy that is essentially zero. If you have something like empty sigma, so you moved, let it be sigma prime, so you moved, you occupy one of the p orbitals and one of the d orbitals, then the energy will be something that is the epsilon of the p orbital of the oxygen minus epsilon of the d orbital of the copper. And S square minus, okay, you don't see this. And this is so-called the charge transfer gap. Or you can have the situation where these are empty and you will have up-down on the copper side. And here the energy will be just U. And depending on whether the charge transfer, I mean, you can draw a picture here that you have this is a single occupancy, and whether the next one is a charge transfer here, and then higher energies are the U, or first U and then charge transfer. That will characterize whether you are talking about charge transfer or a Mott insulator. So if the lowest excitation is from copper to the oxygen, then the smallest gap is this charge transfer gap.
Unlike Mott insulator where there's 2U or U.
Yes.
Here there is another gap.
There is another gap, precisely. Yes, right. Okay, so starting from this, actually this was useful. So we can also try to figure out what happens. And then we can also try to write a perturbation diagram like what we wrote over there for the Hubbard model. How will it look like? It will be more complicated. Yes.
In either case, the picture that you have drawn of large transfer gap was U. In either case, the system is a Mott insulator. Because if there was no U, then what I'm saying is,
yeah.
even if the delta.
Yes, we need you to precisely. Yes, thank you. Thank you very much. Yes.
Mott insulator in any case.
Yes.
That the spectroscopy will see either the gap between the Hubbard band and the oxygen mode, or the Hubbard band and the upper.
Yes, thank you. Yes.
Mott insulator nevertheless.
Right. Okay. So, yeah. Okay, so we have the copper, oxygen, copper, and we start from this here. Upswing on copper. How much time do I have, Subhro? 5 minutes. Okay, 5 minutes shall be enough to get this right. Okay, so we have the two occupied copper orbitals. Oxygen is empty. There is a hopping that will move this electron from copper to oxygen. Then we have some excited state. And it will look like this. Okay, we moved it to the p orbital of the oxygen. So this is the green. This is the p orbital of the oxygen. Right. We could have moved also the other one, but let's keep things simple. Then here, I can continue. I mean, of course, we can come back, but there will be two possible choices. Either this guy is hopping further, visiting the other electron on the other copper side. That will be like double occupied copper side and empty p orbital, or the other copper spin will hop to the oxygen side, and there will be two electrons on the oxygen side. So this is it here, and we have it here. So this will be two electrons here. And then we have the possibility that that the downspin goes here, the upspin remains at the oxygen side and empty here, and eventually we end up with spins that have exchanged their position. So this would be, is it okay? It's going, so this is the state, initial state, this is the final state, and these are the intermediate states. And half of them are missing. So this is the hopping amplitude is TPD, usually people call it TPD. The energy here is just the charge transfer gap here. The energy here is also the charge transfer gap. Here, this is the 2 times charge transfer gap plus U of the p orbitals, which is usually negligible. And here we have the U of the copper. So these are the energies of these diagonal energies of these states, if hopping would be 0, right? And then we can again collect and work out not second order perturbation theory, but fourth order perturbation theory. It's a bit more involved, but what we end up with is the following. So definitely we will have one, here's another TPD, here's another TPD, and one more TPD. So this will be TPD to the 4th power. So the effective exchange is J is proportional to 4 TPD. I mean, the 4 comes from counting the pass. And we have the first intermediate state is the charge transfer gap energy. So this is charge transfer. We have it at the beginning and the end. So that's why we have delta charge transfer to the square, because this one of the T square PD over delta corresponds to this state here, and the other corresponds to here. And then we have the intermediate state, and the intermediate state, which is, I mean, the highest energy or in the very middle, is either 1 over U of the d orbitals, or 2 times this guy, 2 delta charge transfer plus UP. So this would be, in lowest order, the exchange interaction in lanthanum copper oxide, and this is called super exchange process. It's just a name. Right. And it turns out to be, for example, in some of these materials, like I have the value for the strontium copper oxide, for the strontium copper oxide 2, 3. The J will be, this is a linear spin material. The J value is 2200 Kelvin. So this is coming from this type of processes here. Okay, about 1000 times larger than it was the dipole-dipole interaction. Okay, yep. In this, so you see that what we did was to go to oxygens. What also can happen is that this electron starts to propagate and move. It goes to oxygen, it goes to the copper, instead of going to this oxygen, it continues here and goes here and here and here and here and comes back. That would be the fourth order or eighth order or whatever order ring exchange. Now it turns out that for this particular material, if you look at the neutron spectrum, to be able to explain the details of the neutron spectrum, it will be essentially be an antiferromagnet. One would needs to include this four-side ring exchange, and it will be roughly, I forgot the precise value, but it will be roughly between 1 and 10% of the J 2200 Kelvin, 1000 Kelvin. So it is appreciable, it is observable, four-side ring exchange. Okay, I think I shall stop here. This is a good point to stop. And I think I will need to, it's already plan C, what I'm doing now. Yes, thank you.
Thanks, Karlo. Some immediate questions, more questions? Actually, okay, yeah, please go on. Use the mic. Just use the mic.
Are you considering all the d orbitals degenerate? Like you're not taking the different d orbitals?
Very good question. Please come back for your next tutorial. Yes,
You had
perfect.
a question.
They are degenerate. They are not degenerate.
Yeah, I would like to know about the helium structure on a graphene.
Yes.
So you mentioned one thing. If there is a
Graphite. This goes back to 30 years or whatever. I mean, it's old stuff. They didn't have graphene yet. Graphene would be the single layer. They just put it onto the graphite.
Okay.
Yes.
So I would like to know, you mentioned one thing, it could be possible that if there is a ring exchange over a triangular structure,
Yes.
there could be a spin liquid you
Yes.
mentioned. So I would like to know about that. So how that ring exchange process?
Okay. This is right. So it's a non-trivial thing, highly non-trivial thing. I mean, I would not like to enter here. The simplest thing is that what this exchange interaction does is that it will just order antiferromagnetically. Then the next step is frustration, when instead of having a usual antiferromagnetic up-down, you have like a 120-degree order and so on. And if you go further and further, then these ring exchanges will start to play and they will destroy the long-range order. And to show that this is really a spin liquid, you need to have very elaborate techniques. Like, okay, so there were pictures like RVB, resonating valence bond, that is, essentially what it was a counterpart of the ordered state, and it connected like spin up and downs into one thing.
That is what 2.8, right? That is S1 antiferromagnetic. But this ring exchange that
Yes.
You said like this,
Yeah.
DIJK, those processes. So that I did not understand how that could.
I mean, what it does is that it will really mix up your wave function. I mean, if you have like a, I don't know how to answer this question. This is a difficult question. I mean, like, Subhro, do you have a good answer to this?
Not at this point.
Not at this point, okay. He's saving me. Right. So it's really non-trivial why ring exchanges. I mean, what people do is really they look at the exact area. I mean, you really need a very careful study of the systems. And this is a strongly correlated interacting system. A solution is not simple. And you need some different techniques and try to figure out what is the ground state. And maybe, right. I'm sorry. I think this goes well beyond the, but maybe I don't know. Yasir is also he's hiding there.
You're asking about the possibility of realizing a quantum field with effective derivation
Yeah, like for a S1 dot antiferromagnetic Ising kind of interaction on a triangular lattice, we can have spin liquid.
Can you talk to the microphone, please?
Yeah, but with this ring exchange process, that is something new for me, and I wanted to know how this could lead to such.
No, ring exchanges are also frustrating exchanges. So on the triangular lattice, they could also realize, they could also melt long-range magnetic order of the 120-degree type. And you could realize a state which has no long-range dipolar magnetic order. And there have been studies trying to propose one has to do actually a really systematic study of all possible quantum spin liquid answers for a given model with a ring exchange. Then try to answer the question of what is the optimal ground state of the model. But so this is a careful study, as Karlo said, using many numerical quantum many-body approaches.
Okay.
It's going on for 20 years, 30 years, 40 years.
Okay.
So did this helium-3, they got a Nobel Prize for this thing. So it is going on for like, what is this, 70s, 80s maybe, 80s. And when people try to look at this ring exchange, how to calculate it with Monte Carlo, that is from the late 80s.
Okay.
Like Zeppeli and, yeah.
Okay, yeah, I'll look into it, yeah. Thank you.
Yes, I'm sorry that I cannot provide a more detailed answer at this stage.
More questions? Is there any question from the online participants? You can unmute yourself and ask the question. We would be able to hear you. Okay, doesn't look like. So let's thank Karlo for part 1. And so we gather like 10 minutes to 12 and have Karlo's part 2. Okay. Yeah.
And the tea and the coffee are just served in the foyer, just on the right.
Okay, so you moved certain degrees of freedom to move from the Hamiltonian to the effective Hamiltonian. So we probed the lower system. Can we use the same method to probe the upper system? So we can remove the lower degrees of freedom and keep the higher degrees of freedom.
Yes, thank you very much. This is a very important question. Actually, what I showed you, this perturbation theory is kind of difficult and not so easy to do. There is a more systematic way how one can do this transformation. It is using canonical transformations. It is like in the quantum electrodynamics, it was called the Foldy-Whitehouse, but applied to the solid state physics is the Harris-Lange or McDonald or whatever. So there is a systematic way how, if you have a Hamiltonian that has like a U, that is the largest term, there's a hopping, and then there are other terms that you expect. One can apply a canonical transformation that will remove the hopping part, and as a result, T square over U like Hamiltonian terms will appear. And they will be precisely those terms that we derive using the second order perturbation and additional ones, and they will tell how the high energy, like the splitting between the splitting that you saw, there was a double, the U energy and the small splitting T square U there, it will be able to also describe that part. In addition, if we apply the canonical transformation to the operators as well, we will get corrections to the operators that will also describe these additional degrees, this higher, the effect of higher bands. For example, if you apply to a density operator in this picture is very simple, but if we apply it to this canonical transformation to the density operators will get a part which will describe this this higher higher energy states as well. So if you want to do, say, or these density operators will also get a spin spin operators in it. So it will be like density operator plus d over u times some spin operator or something like that. And then using this, the density operators will depend on actually what are the spin configurations. So this is very powerful method. And just look at the Harris-Lange or Kankar transformation effective models. Yes. Good. Thank you for this question. And maybe there was some other, but okay. Right. So what did we do the last lecture? Perhaps you still remember that there was this picture, that there was the d orbitals of the oxygen, of the copper. There was the oxygen p orbital, and there was another copper orbital. And what we discussed is that there is a fourth order process, the so-called super exchange, which will give us the exchange interaction between the spins on the couple sides. Another question was, is this important? Why is this so important? So the thing is that usually, very often, the Mott insulators are in a ionic solid. So typically we have some transition metal like copper, iron, nickel, whatever, and oxygen or sulfur or some other material. So these are typical very ionic solids. So for example, in the lanthanum 2 copper O4, I hope this is Harald. Is this 214? Yeah, thank you. Sorry for disturbing. Yeah. Right. So in this material, the oxygen is 2-, so it will fill its shell. It is inert, and it will take the electrons from the copper, and that's why the typical average occupancy of the copper is 1 whole. To be more precise, 1 whole spin. Also, okay, fine. Now we derived that there is a exchange where the effective Hamiltonian is J times S dot S, and maybe I write here SE, where the super exchange is positive. Positive means that if it was negative, we would like to maximize the spin, and that is leading to ferromagnetism, that all the spins are pointing in the same direction, but if it is negative, it does not. There are other possibilities, so there are many chains. And for example, there will be a chain where the oxygen and the copper is in a different geometry. For example, it will be something like this. This is the copper d orbital. If you want, I can write it dx squared minus y squared. Then here is the oxygen. Say this is the px orbital. Then there is another orbital. This would be the py orbital. And here is another copper ion. What happens in this case? Let's try to figure this out. So what we do is that there is an electron here, and we can try to draw the same type of, that has been deleted, the same type of effective interactions. So we start from a case when we have 2 copper levels and the oxygen level. There are now 2 oxygen levels. There is the px and py. And there is some spin configuration here. Say this is the px. You can't see it. Is that right? I shall write it bigger so that you can see it. To say px, they are same energy, but py, and there is these are the copper, and this is also the copper. This copper is connected to px orbital. It can't hop to the py orbital because if you look, there is a reflection mirror plane here, and they have different symmetries. This symmetry is such that it is even under reflection, and the py orbital is odd. So there is no hopping matrix element between this d orbital and the py orbital. It can only hop to the px. So there is only a single hopping here. Similarly, from the other copper ion, we can only reach the py orbital. So these are the only hoppings that are allowed. In other words, the situation that we had over there about the super exchange, that very complicated graph, and I've only drawn half of it, becomes much simpler. What happens in this case? The main difference is that, for example, if an electron starts its journey from copper to oxygen, it can't propagate further. It will go back. So let's try to look at it. So there is one up spin, and let's put here down spin. So the first intermediate state is that we have moved this guy to one of the oxygen levels. For example, here. And then we move so that the two spins see each other. We move the copper spin electron from the second copper to the oxygen orbital. And then what we will have the following situation, that there will be two empty copper orbitals, and there will be two spins on the oxygen sides, but on two different orbitals, right? What is the energy of this guy here? My plan A was to derive the so-called direct exchange, which I will not do because I don't have time for that. You will take my word for it, or I just refer to the Hund's rule. It says that if we have two electrons on two orbitals that are different, we would like to have a maximal spin state. So there will be an energy difference between the states where these two spins make a spin 0 or spin 1 triplet configuration. So if the two electrons are forming a triplet, this is what we want. This will have energy J Hund, while if they make a singlet, they will not contribute, and they will be in a higher energy state. So this is very different from what we had in the case of the Hubbard model. So if we have two orbitals that are orthogonal to each other, the electrostatic energy, the Coulomb energy, would like them to be in a maximal spin state. The maximal spin state is a symmetric wave function. Maximal spin state is up-up. The full electronic wave function is antisymmetric. Electrons are fermions. So if the spin part is symmetric, the orbital part needs to be antisymmetric. And it means that we are not going to occupy those orbitals. We are not going to occupy the same orbitals, but we are going to occupy the different orbitals. And it will give us a possibility to lower the Coulomb energy, the electrostatic energy, because then the wave function is more spread. So the statistics, the Pauli statistics, and the Coulomb energy in case of two orbitals that are orthogonal to each other will lead to the ferromagnetic exchange, and these are the Hund's rule. Hund's rules, one of the Hund's rule, which says that we want to maximize the spin here. So if we look at this process here, then it will turn out that the energy is the following. So we can have, if they were in the singlet state, right? So I will write down something and then I will try to explain, okay? So I need to draw here the final steps that you can imagine what is going on here. Down is here, and up was up there, and then we will have the final step when they exchange. This is down, this is up. Okay, so so this is one configuration so that you can separate the configurations. Right. So the energy is proportional to dPd to the fourth power divided by the charge transfer gap to the square. This is because this is this process that we have one electron from copper to the oxygen side, and also there. So this is coming from that. And we have here 1 plus 2 delta plus V plus J Hund over 2 if spin is equal to 0, and T4 PD over delta square charge transfer. And here, actually I don't need this, 1 over 2 delta plus V minus J Hund over 2. This is if spin is equal to 1. The total spin is 0 and 1. So this is if they are ferromagnetically aligned, they make a triplet. This is a singlet. And what I have written here is the energy of this state here. So 2 delta, because we have both p orbitals occupied, that's 2 delta. We have a V. The V is not the U. The V is the Coulomb repulsion between the electrons on the px and py orbitals. So if px and py orbitals are occupied, then there is a different Coulomb repulsion than between if we have 2 electrons on the same orbital, and this is called V. Or you can say like UAB, or there are different notions. And the difference is in this part here. This is the Hund's rule. This says that if the GH is positive, so if the 2 spins are in a triplet state, it will have a lower energy than if they are in a singlet state. So the effective interaction is then the difference of these 2 guys, because this is a singlet, this is a triplet, and the exchange energy is just the energy difference between the singlet and triplet. So we can write that the J effective in this case is proportional to minus, okay, there are some numbers, okay, I don't write numbers, TPD to the fourth power divided by this transfer gap, 1, 2 delta plus V minus J Hund over 2 minus 1 over 2 delta plus V plus J Hund over 2. Fine. And this is minus 3 to the 4 power divided by delta square charge transfer, J Hund over 2 delta plus V square. Right. So this, I mean, I expand, J Hund is typically the smallest, the V and delta are larger, so we can expand. So this will be an effective ferromagnetic exchange. So if we have a material, and we have many of them, I will show you in a couple of minutes. In that case, or maybe in half an hour, there will be, okay, so typically what we may have is that there is a copper side, there is an oxygen side, another oxygen side, another copper side. And it continues. And say this is kind of a chain. There are such chains. And depending on how close the copper side and the oxygens are, this angle can vary. It can be 90 degrees, but it can be bigger or smaller than 90 degrees. So if it is different from 90 degrees, then what happens is that if it is precisely 90 degrees, then there will be no possibility from, I mean, the electron will hop from here to this oxygen side, it cannot hop further. But if the degree is not 90 degrees, but some larger amount, in that case, then it will be possible for, just think about it that this is maybe, I draw with red. So this is here the, I mean, you see this is slightly larger than 90 degrees. In that case, we hop here, and there is no, this mirror axis is lost. So there's a possibility to have that this electron hops further to the copper side here and back. So we have a combination of super exchange and this 90-degree ferro exchange. So depending what is the angle, one can very finely tune the J's from antiferromagnet to ferromagnet. Right, good. Okay, this was the 90-degree exchange. Any question about this? Okay, good. Fine. The title of the workshop is Itinerant and Insulating Mott Insulators. So I would like, there will be some talks that will also present what happens in lattices in systems where you have localized spins and itinerant spins. And that is the so-called double exchange. And I will show you one example for that. And that the most important material is the manganese oxides. Before going to manganese oxides, there was a question if all the d orbitals are degenerate or not. Somebody, maybe you asked it? No, somebody else, somebody asked, yeah, you asked it, yes, right. Okay, so they are not. And let's look at that at this moment. Okay, so the message here was that in the intermediate state, in the case of antiferromagnetism, the double occupied side that was favored was in a singlet state, but here in the 90-degree, it was in a triplet state, okay? Just before you forget it fully. Right, yes, okay, so d orbitals. So typically, I mean, let's look at the example of the lanthanum 1 minus x, strontium x, mangan O3. Right. The lanthanum and strontium have different valence, so changing the X composition, you can dope the material. So in one case, it will be maybe insulator of one type. If the X is, say, 1, it will be something else, and in between, we will have itinerant delocalized electrons. So what happens in this manganese oxide? Manganese, in this case, is sitting in the middle of an octahedron of oxygens. Here are the oxygens, here, and oxygen here. This is behind, and I'm just closing the octahedron. So can everybody see that this is an octahedron? Okay, so this is inside, manganese is in the center of octahedron. This oxygen, there are 2 minus, these are ions. So they are negatively charged. Now the manganese, the important manganese orbitals that play in that are important in this case are the 3 d orbitals of mangan, and we have 5 of them. If this pure manganese atom would be in space and it wouldn't talk to anybody, so this lonely manganese would have 5-fold degenerate d orbitals because it would be in perfectly isotropic space. But here it is not. It is surrounded by these oxygens, and it feels the electrostatic energy of these oxygens here. And not only the electrostatic energy, but also the overlap, the T overlaps are different. So, and it is very convenient to use the following basis: dxy, dxz, dyz, dx squared minus y squared, and d3z squared minus r squared. So these are the 5 d orbitals, which are, if we write it like that, these are all real wave functions, real in the sense that they are not complex. They are real, and you can kind of represent them that here I draw the x, y, and z axis. And this xy is something that is maybe, it is, yeah. So there is a positive cloud wave function here, and there is a negative wave function. Let's use it. So the red will be the orbital. So there is a positive here, and the negative part along this here, something like this. So do you think you can see this? Yeah. Everything is okay. So yes, very good. Let's do it in the xy plane. So in the xy plane, yes, in the xy plane, this is it. Of course, there is a R-dependent part, and I am simplifying a lot. But essentially, this is the main idea, that in the xy plane, if this x times y is positive in this region, x times y is positive here. If we take a number from here and here and multiply, this will be positive. It will have a nodal line for y equals 0 and x equals 0. So this is becoming 0 if x or y are 0. And it is negative for y positive, x negative, or y negative, x positive. So this is something that has a positive, negative, negative, positive. So this is the shape of the d orbital. Those three orbitals here, they are such that they will have this symmetry on the three different planes, xy plane and xz plane and yz plane, okay? And you can think that they are kind of behaving similarly if we put them into this cage of oxygen, because what happens is that this octahedron has the cubic symmetry, and it transforms. I mean, the cubic symmetry. It means that it is like so-called OH, and there are 48 group elements. So it is very high symmetry, and if we say rotate the whole thing by 90 degrees, we get the same thing. And if we rotate these guys by 90 degrees, they will change, for example, one plane from the other to the other plane, and so on. And they will have all the same energy. So these orbitals, they are equivalent under the OH symmetry. So you see what I mean is that this is, I mean, if you think I will try to draw the octahedron on this picture here, that there will be an oxygen around here and above and below. And then if we rotate the whole thing, the oxygen will be on the same place. I mean, they will be the same position, but the orbitals will turn from the plane of the blackboard orthogonal to it, and it will be the same energy. You can imagine that. Is it fine? Okay. So these three orbitals, they are so-called T2G orbitals. They are called T2G orbitals. They form a three-dimensional irreducible representation of these manganese d orbitals in the crystal field of the surrounding oxygen ions. So this is the crystal field split orbitals. Right. X squared minus y squared. Okay, so this was the dxy. This is the dxy. And you can guess what the dx squared minus y squared will be. We need to have positive, and this thing is positive, so it will be something like this, and something like this, and this will be positive here, and this is negative. This is the x squared minus y squared, and z squared minus r squared is such that it will be like a donut in this plane, and there will be some globe that is outside for positive and negative z. This is a two-dimensional manifold, two-dimensional lattice representation, and these are called the so-called EG orbitals. Right. If we reduce further the symmetry, there will be further splittings here. When you ask about the copper, there was the plot, I draw the lattice of the copper, lanthanum copper oxide. It was something like this: copper, oxygen, copper, oxygen, copper, oxygen, oxygen, oxygen. So here you can see the 4 oxygens around the copper, and there are 2 other oxygens around the copper. One is above and one is below, but they are not the symmetry equivalent of those 4 oxygens. So this octahedron is kind of squished or elongated or whatever. In that case, these levels would further split, and the important orbital is one of the EG orbitals that is important for the copper, lanthanum copper oxide planes here. Okay, so we have these guys here. Now let's see what happens in the case of the manganite. Free z square. Yes, okay. So, yes, no. Okay, so this is very good. So free z square. R square is minus x square minus y square minus z square. So it is something like 2z square minus x square minus y square. So you see that it's positive if z is, if we are going in the z direction, up or down, and it's negative if it is in the xy plane. And you see that there is a rotational symmetry. This is like a R. So if you would like to draw this guy, it would be like, maybe I will try to do it. So this is like Z, X, and Y. So it is positive for Z. So we will have something that is like here. This is like 2 globes, and there's a ring around it. That's where it is negative. I don't know how much you can see it. So there are like 2 globes, positive, and there is a ring around it that is negative. That is this Vz square minus R square orbital. Is it okay? Yes, good, yes. Okay, perfect. Right. So manganese. The electronic structure of manganese in this material there is such that there are the T2G levels and there are the EG levels. So I'm talking about the manganese atom in octahedral environment. And I should say that this is manganese whatever plus, but I forgot. There are the 2 EG levels. And depending on the doping, either we have a situation when the T2G orbitals are filled, and there is one additional orbital, additional electron on the EG orbitals, or a situation where only the T2G orbitals are filled. I have drawn these spins pointing in the same direction. This is because of the Hund's rule. We discussed the Hund's rule for the case of the oxygen, and it also is valid here that they would like to maximize the spin component, so they will make S equal 3½ moments if the 3 electrons are on these T2G orbitals. This guy is also related by Hund's rule to the other guys, but Hund's rule these three electrons are really making a very nice, almost isotropic 3½ spin. It is this shell is kind of filled. So if we can think about this as a localized spin of speed 3½, and then there are these electrons which are either present or not, and there is another EG orbital, and they can hop around. Okay, so what is the effective model for this system? Yes. Right.
This is reverse order of orbitals energy diagram.
I have it like this in my. I don't know. Maybe it's possible.
What I mean to say is, you might just interested students. T2D orbitals have lesser repulsion. They experience lesser repulsion from the oxygens which are sitting at from the X, Y, Z direction. Their energies are lower, and the EG orbitals experience more repulsion. Their energies are that is the correct picture in this case. I mean, in this case of that depends on the denominator or sorry? That depends if the operator is denominated or no, that's right. But I'm saying is only that.
Right. Okay. Yes. Sorry. Okay. So this is not an energy axis. Yes. Right. Yes. So.
And what you have drawn is if it were energy axis and if it were tetrahedral field, then it would be okay.
Yes. Okay. So there's a reason why I draw it this way, because usually this is a kind of a contour lattice model. In the contour lattice, okay, yes, Yogesh is right. I should have, if I think about this, usually all these plots were such that he was low energy, high energy. Thank you. Yes, you're right. Yes. Yeah, right. So, yes. Yeah. Okay, right. Yes. Here are the conducting electrons. And the Hamiltonian is as follows. Minus T times C dagger C I sigma J sigma plus Hermitian conjugate minus J Hund times alpha beta C dagger alpha site I S dot sigma alpha beta underscore C beta I plus U times sum Ni up, Ni down. Yes, what is this? Here, this describes the hopping of the EG electrons. Right. This describes the Coulomb repulsion of the EG orbitals. This part here describes the Hund's rule between the T2G s equal 3/2 spins that we treat as localized times the spin of the itinerant electrons, which is nothing else but this C dagger alpha times sigma alpha beta Pauli matrix times C beta. The alpha index is going over the up-down spin, and the beta is also going to up-down spin of the spins of the EG orbitals. And when we combine this C dagger alpha, sigma alpha beta, C beta, that will give us the S matrix. So S mu, this is the spin of the spin 1/2, is equal to C dagger alpha sigma mu alpha beta C beta sum over alpha beta. So we take the spin up down of the electrons, we take the Pauli matrix, is the XYZ Pauli matrix, and we make this multiplication, and we have the C beta from here that will multiply the lower index of the Pauli matrix, and mu Pauli matrix is telling us the spin mu component of these 1/2 spins. Let's see an example, because you don't seem happy.
Karlo, I have a question. So the reason you have not written the bare exchange terms within the T2G manifold is that they're usually negligible.
They're not.
Huh?
They're not.
They're not. But they also have a component where you integrate out the EG.
And these are very important. Thank you.
Okay. Thanks.
Yeah. Yes. Thank you. So clear. So let's see how does this work. So the SZ of the itinerant electrons is equal to, we look at the sigma Z, the Pauli matrix sigma Z is just 1 minus 1. Maybe there is 1/2 here. Let's write here 1. It depends how you define your sigma. So this is it. So it will be 1/2 times. We have only the, and here, this is the up sigma Z matrix element. This is the sigma Z down. Is it fine that what I write here? Okay, everybody? This means no, yes. Not very happy. Okay, so right, so you have like the problem with the big linear board is that the sponge is far away. So here we'll have the up component, here we'll have the up down. That's right. Down, and down, up. Something like this. So these are the different parts in the sigma. Yeah. Right. So if the sigma Z has only up, and down, so it means that if we look at the sigma Z, so there will be only up, and that will be positive. So it will be just C dagger up, C up, minus C dagger down, C down. And that is equal to 1/2 and up minus and down. Very good. This is something that is already more familiar. I mean, the SZ component is just the difference of the occupation of up spin minus the down spin. Good. If we look at the SX or S plus, it will be just like, for example, S plus will be just C dagger up, C down. This would be the S plus operator, where sigma plus is just like 0, 1, 0, 0. Now I don't know where is the 1 here or here, but something like that, okay? So this is what is standing here. So this is the model that people look at when they want to describe the manganese oxide or other materials where we have localized spins and itinerant spins. So, and this is called a condor lattice. Loosely speaking, the real condor lattice is with negative, with antiferromagnetic exchange. And this is the interaction between this is the hopping part of the itinerant electrons. This is the coupling between itinerant and localized electrons. And there is also exchange interaction between the localized spins. Okay? How do you feel about this? Right. What does this know? What is it able to tell us? So, okay, so let's concentrate on the two cases. Maybe here. This is the free half spin. Again, a free half spin. There is one electron that is on the EG orbital that is parallel to the spin free half spin. And another spin free half spin is parallel to this guy. So this spin can freely hop because the energy before and after the hop are equal. On the other hand, if we have a situation where we have the large spin pointing in the opposite direction, then this guy that is parallel to the free half spin, if it would hop, it can, during the hopping, we don't turn the direction of the spin. It will be in the antiferromagnetic it will be opposite to the large local spin. So it will lose Kunz energy. It will lose a lot of energy. So if it wants to hop, it's difficult to hop because it needs to invest energy. So it means that if all the spins are parallel, then the electrons can freely move in the system. If it is an antiferromagnet, then they become localized. They cannot hop. And in this case, the resistivity is much lower, much higher. Okay. And we can also turn a little bit the picture different. We can say somehow differently that if there is a sufficient number of itinerant electrons, they are, and this J is not sufficiently large, in that case, the itineracy of the electrons will make the local spins ferromagnetically aligned. So this is itinerant electrons driven ferromagnet here. And in this case, it is not going to happen. This double exchange is something that is used in the hard drives. So this is the mechanism. I mean, if you make your head of your hard disk from a material that is like this, in that case, depending on the magnetic field of the plate below, I know today we have SSDs, but earlier the resistivity would very drastically depend on the magnetic field, because the magnetic field will interact with these localized spins and try to make them more ferromagnetic, and it will decrease the resistivity, to decrease the conductivity. And these guys are called, they have a so-called colossal magnetoresistance. So if they check the resistivity against magnetic field, their response is huge, much larger than, because there was a gigantic magnetoresistance that was for multi-layers of different metals, but this was even larger. So this has been studied like 20 years ago. Yes, please.
Do we know of systems where the J physics and the Hund's physics compete?
Even in this material, they compete, because you will have antiferromagnetic phases and ferromagnetic phases, depending on the how large is the doping.
I see.
Yes.
I see.
So essentially, when there is no doping, then it will be more antiferromagnetic. If you introduce doping, there will be. So the phase diagram is very rich of this material. Yes. How do I stand with time? Badly. So I think we have like half an hour. Right. Okay. Good. Fine. So far, okay. So there were these T2G orbitals, and okay, everything that I was telling you until now were isotropic magnets. So the spins didn't. I mean, we have S dot S here, and so on. So they were all isotropic. The spins didn't know about the lattice. But there will be cases when they will know about lattice, and that is when the spin-orbit coupling plays a role. So before you asked me, I think, for example, if you put this term into pyroclass, in that case, you will get all, probably Motomé-san will give a talk. The reason I'm mentioning it is that there will be a talk by Motomé-san about itinerant such systems in frustrated environment, and then it gives rise to very, very, very interesting phase diagrams and phases of matter, right? Okay, so spin-orbit coupling. Spin-orbit coupling is a relativistic effect. What happens is that, okay, so yeah, first let me delete it, and then this is plan D, or E, or whatever. Good. I also wanted to show you some slides, a few slides. I'm hesitating what to do. Do you think we can lower the screen, please? Right. While it's getting lower, I will try to explain the origin of the spin-orbit coupling. Suppose that you have an atom, and there is an electron orbiting around it. Z, there is an electric field that is keeping the electrons in the orbit. Now, if the electron is traveling in this electric field, and we sit on the electron as it goes, it will experience an effective magnetic field in its own local frame of inertia. What? In its local frame. So, if an electron or charge, a moving object with velocity v is propagating, is going in the electric field with some velocity v, then there will be, it will experience a magnetic field that is proportional to E cross V. Okay, so this electron will feel a B that is proportional to V cross E, something like that, and this B will interact with the spin 1/2 of the electron. So, and this interaction will lead to the so-called L dot S term in the Hamiltonian. This will couple the orbital momentum of the electron. L comes from for the d orbitals. It can be L equal 2, so it will have L equal to moment that is interacting with the spin 1/2 moment of the spin of the electron. Or for the p orbitals, this would be 1, the L is 1, and this would be 1/2. For f electrons, this L is free, and the S is equal to 1/2. And this term is larger. The heavier the nuclei is, it goes to the Z to the maybe 3rd power, and it becomes important for the 4D and 5D and essentially 4F electrons. We were talking until now, usually manganese is 3D or copper is 3D. In that case, this is not so important. But for heavier elements, this is important, and it will connect the spin and the orbital moments. But now, since I have the screen, I would like to share it, and I think I need to share my screen. And okay. Aha, you see something. Let's see, I have a few keynotes here. Okay, so this first keynote, I forgot what, maybe I need to play. Let's see if it works. Do you? It's always a trouble. I hate this. Really hate this. You see that I didn't give too many Zoom talks. I don't know what to do. I'm sorry. I hate this. I really hate this. Can you help, please? No Hebrew, please. So until that, this is getting fixed. I may maybe stop sharing and start. We tried in the break. It worked in the break. He made it work. But maybe we leave it like this. I see something. This is okay. Right. Okay, so this was just a paper from, yeah, thank you. Just pointer. Yeah, right here. Okay, so this is the lantern copper oxide. This is the parent material antiferromagnet. You see the copper oxygen plane. And these are the oxygens above below. You can see that this is the blue is the copper, and it is, you don't really see it very nicely. So there is this oxygen, copper here, and there are the 4 oxygens around it, above and below. And this is the octahedron, and these are the possible passes. And people did neutron scattering measurements. It measures the dispersion of the excitations of the underlying spin 1/2 antiferromagnet, and to be able to describe precisely the modes. What you see here is that this should be flat. In the very naive calculation, when we have only nearest neighbor exchange, this mode should be flat, but it is not flat. And then Radu Kolder and other people, they invoke the Forsyth ring exchange to explain this behavior in the spectrum. So you really need to do some elaborate experiments to see this. What else is here? Okay, I think I will skip this. And let's go to the next here. This is about the colossal magnetism. I mean, this, well, this is what or shall I not? I just place this here. Okay, very good. Now, this is the phase diagram of the manganites. And what you see here, this is the X. This is lanthanum strontium mangan oxide. This is the energy level scheme. Yogesh, you were absolutely right. This is the as correcting with the energy. And there is additional further splittings here. But essentially, there are the S3 halves and the itinerant electron here. And this is the phase diagram. So if x is around 1/2, then in that case, the itinerant electrons are missing, and in that case, we have an antiferromagnet made out of the free half spins. If we decrease it, it becomes ferromagnetic, and then there will be other phases like charge is commensurate. Sorry, I forgot what are the Ci and Fi's. So very complicated phase diagram, and you can replace the lanthanum with neodymium or praseodymium and strontium with calcium and so on, and then you have different phases here. This is the resistivity against magnetization, and this is, you see if the magnetization is growing, it means that the spins are pointing more and more parallel, the resistivity is dropping. So the more parallel the spins are, the smaller the resistivity, the larger conductivity is. Okay, good. Okay, this is different. And then the 90 degree, where is the 90 degree? I hope I didn't close it. Super, yeah, this is it, perfect. Yes, so this is super exchanging cuprates. So this is the susceptibility as a function of temperature. And from this, they extract that the effective exchange in this strontium copper oxide, this is the material itself. You see that it is made out of chain. Copper, this is the copper here. And the oxygen is the black disk. So we have kind of chains of copper ions. And they are separated by the strontium ions in between. So this is a 1D chain. And in this case, the effective J is 2000 Kelvin. This is another example. This is strontium copper O2. And here, what happens is that it is like a zigzag chain. And then it is like it depends how you look at it, either 2 decoupled chains or weakly coupled chains. Now, what you see here, this is the copper, lithium to copper O2. This was interesting in the late 90s. Here, the copper is, the oxygens are these empty disks. These are the copper is the black disk. And you see that we have these almost 90-degree bonds here. So what happens is that there is a very weak ferro or antiferro interaction between the first neighbors and a second neighbor interaction that is roughly of the same size. So we have a competition between the nearest neighbor and next nearest neighbor, coupling in linear chains. Here, this is an experimental plot of the effective J1. In materials, there are different chain materials, and the theta angle between the copper, oxygen, copper path varied from 80 to 100 degrees, and you see that there is this region where it is ferromagnetic around 90 degrees, and then it really very sensitively depends on the degree, right? So this is about the 90-degree exchange here. Yes. And I think this was all for the moment. Thank you. I think this was all. Thank you. Good. I think we can perhaps raise the screen. Right, good. So we need to understand. There was one more. Is it still alive? Is it still alive? Let's see, one moment. I had one more. I had one more. Where is it? The DM interaction. Yes, this one. I need to share my screen. Oh, yeah. Launch meeting. Hello. Sorry. Come on. Share screen. And I need only one slide. And yes, this here, this one, only this. The first one. Yes, this is it. Right, okay, so this is a Jaroszynski-Maria interaction. Is coming from the spin orbit coupling. So what you see here, this is the material iron 2O3. It is essentially iron atoms that have large moments, 5½ and yet it showed a weak antiferromagnetism, and people didn't know why is it there. And then Jaroszynski looked at the symmetry of this magnet, and he considered what are the symmetry allowed terms in the Hamiltonian that can be present. And when he looked at these terms, he found out that there is a term of this form that is by symmetry. This is a lower symmetry compound. It is distorted. You see that it is very stretched. And he added this term here, which what it did, this term, is to count the spins. And so we have essentially an antiferromagnet with little bit canted spins. I will, if I have time, I will derive this Hamiltonian. And in that case, there was a weak antiferromagnetism. And this this term, Jaroszynski, it's called Jaroszynski-Moria interaction. Jaroszynski derived it using symmetry arguments, but Moria, in next year, he derived it using microscopics. Microscopic derivation involves taking into account this term here, and it is quite involved, and I will not reproduce it here. I will only present the symmetry argument. I'm finished with the presentation this time. Thank you very much, and sorry for this interruption. Right. So let's try to figure out how does this work using symmetry arguments. The name of that crystal iron oxide is hematite. Right, so suppose that we have a bond where we have a copper, another copper, and then oxygen that is off the center. So we had the superexchange when the oxygen was precisely in the center, but it may happen for different reasons that it's not in the center, but it's slightly off. What happens in this case? What are the possible Hamiltonians that we can have? So what is the symmetry of this problem? What we have, there is a winged axis. So the axis is as follows. This is the x, so the bond is around the x direction. The oxygen is out of from the center in the y direction. And we have the z direction coming out of the plane of the blackboard. The symmetry is we have a C2y. This is side 1, this is side 2. So this C2y is rotating our system around this axis. So the copper will go to copper 2 and copper 2 will come to copper 1. This is fine with you. What other symmetry do we have? We have a mirror plane. The blackboard itself is a mirror plane because if we apply the mirror to this picture here, the oxygen stays where it was and the copper stays where it was. So let's see what happens if we apply the C2y and the sigma. I will denote the sigma with sigma xy. So the x and y are not affected by the plane. So how much time do I have? Okay, good. C2y sigma y, and let's see what happens if we apply to x, y, z, and Lx, Ly, Lz, or Sx, it could be a spin component, it doesn't matter, and side 1 and 2. So the C2y, it makes a twofold rotation around the axis that is in the plane. So it will change y 1 to 2. So one side becomes 2 and side 2 becomes 1 under this rotation. Okay. The y-axis is not affected by rotation. The x-axis, if we were pointing something in this direction, it will be pointing in the opposite one. So this is minus x. And similarly for the z, it will be minus z. Now, how do I transform the spin operators, the momenta? momenta are not vectors. X, Y, Z, these were components of a vector. The magnetic moment is not a vector, it's an axial vector. You can think about it as some rotating electron. Rotating, and let's try to do the mirror compared to this plane of the desk here. So it is rotating in this way, and the mirror image is rotating in the same way. So the component that is orthogonal to the plane does not change. The component that is orthogonal to the plane does not change, and that is the Z component. So here I shall write L. Is that right, what I'm saying? It's right. Okay, yes, it's right. Good. If this is the mirror symmetry, if I have something that is rotating this way, I will try to do it. It's not so simple. You have something like this. It means that in one case it's pointing to the left, in the other case it's pointing to the right. You see this? You can try to, yeah. Right, so the Lx and Ly component will change. I'm sorry, I screwed it up, it goes here. My apologies, I was talking about the mirror plane here. Mirror plane here, it comes here. Right, so the LZ was fine. The Lx and Ly got minus sign. Yes, like this. I need to be careful because time is running. This is right. You think? Okay, good. Right. Here, what we have is that sigma xy, this remains, this changes sign. Okay, good. And the C2y is just rotating things. So if I'm rotating this way, it will follow. So it will, I mean, under rotations, the pseudo vectors, axial vectors, and the vectors, they transform the same way. So it will be minus Lx, Ly, and minus Lz. So these are the symmetry, the transformation of the vectors and axial vector under the rotation around y-axis and the xy plane. Yes, perfect. Thank you very much. Right, very good. Now, what is the possible Hamiltonian that we can write? So the H, we can write H as a J alpha beta, S alpha as beta. The Hamiltonian needs to be invariant under the symmetries of the problem. Now including special symmetries because we have a connection between the spin and the orbitals. Let's see what happens to the, can we have XY orbital, XY, XZ interaction? So we have like, I should have written SZ, but anyway, so this, yeah, good. So this can be L or it can be S. L or S, they are the same. I don't want to make a mistake because time is running out and I have written here the next S. So if we have S1, S2, Z, and we apply the sigma XY, this guy here, then what it will do is that it will not affect the order of the spins. It remains the same. So it will be JXZ, S1, S2, X will get a minus sign, and the Z will get a, thank you. X will get a minus sign, and Z will not get a minus sign. So this will go to minus S1X, S2Z. So clearly, we have changed the sign of this term in the Hamiltonian, and because of that, this can't be in the Hamiltonian. Let's look at another one. Let's look at the JXY, S1X, S2Y, and again, we look at the sigma XY. What it does is that XX and SY are both changing sign. So this is allowed term. Right? Minus SX minus S2Y, which is equal to JXY, S1X, S2Y. Very good. This is allowed. We can go through and check what is allowed under sigma xy, and it turns out that the Hamiltonian that is allowed, and here I'm only writing the off-diagonal parts, I'm not talking about the JXX, it will be the JXY, SX1, SY2 plus JYX, S1Y, S2X. Okay? These are the two terms that are allowed by sigma. Now, let's apply also the C2Y symmetry element. So what it does is that if we apply the C2Y to the JXY, SX1, S2Y, what it does is, I just write this here, it will exchange the side indices. 2 becomes 1 and 1 becomes 2. The X will become X and Y. Let's see, X and Y. X and Y. One of them is changing sign. So this will be minus here. And this is X, this is Y. Is this correct? Right? And we can rewrite this as minus JXY, S1Y, S2X, which is the same, and the corresponding term in the Hamiltonian, and this needs to be equal to JYX, S1Y, S2X. So from here, we got the condition that these two coefficients in the Hamiltonian needs to be equal. So it means that if we also include the C2Y, in that case, the Hamiltonian becomes JXY, S1X, S2Y, minus S1Y, S2X. And this is nothing else but the so-called S1 cos S2 times D, where the D vector is pointing like 0, 0, Z. This is the D vector. So this is how we can derive, and how Jaroszynski in 50-something, 8 maybe, derived the effective possible allowed symmetry, allowed Hamiltonian for the hematite, for the iron 2 oxygen 3. Is there any question regarding this? Wait, microphone is coming.
Why we did not change minus jxy to jyx in that case when we were doing for the mirror plane?
What did I, what? So here,
Yeah.
what, I mean, here, I'm not sure if I understand your question correctly. You mean that there is some problem?
Yeah. So there we said that that is not a possible case. Like,
Yes, that we can't have it because it changed its sign. No, this one here. Yes, we can't have it because we have, I mean, we have the same sides, and if we apply the xy term, what happened is that it changed the sign of the xy. It changed the sign of the x component. So this became negative, and that is the sign here. So we have this term in the Hamiltonian, we apply the symmetry, and we get the negative of that term.
yes. So, like in that case also, what is
the difference is that here we had a different, I mean, we are trying to, we applied this term to the Hamiltonian. I mean, this is the term in the Hamiltonian, we applied the symmetry, we arrived to this one, but this is not the same because we have the different indices. So this can be recast into this form, but this form already exists in the Hamiltonian, but with a different coefficient. So if we want to allow this term to exist, we need to allow for the JYX term to be negative of this.
Okay.
Because then it will survive this symmetry operation. Does it?
Yes.
Right. Okay, so how much time? 0? Minus epsilon. Okay, so let's stretch this epsilon a little bit. Just a few remarks. So what you saw here is that if we have this oxygen not in the center of the bond, but slightly off, then there is a term that appears which is proportional to the S1 cos S2. This term, this is a triple product. It wants to span a volume with D, S1, S2. They want to have a large, I mean, they don't want to be in a plane. They want to span a volume if possible. So if we have a configuration when, I mean, this typically arises next to an antiferromagnetic exchange. Antiferromagnetic exchange wants to make the spin antiparallel. And this term would like to have some finite volume. So suppose that the D vector is pointing out. So what it will do, it can gain volume if the spins start to tilt a little bit. And if they tilt, then the DM interaction, they will reach some compromise between the DM and the Heisenberg exchange, and this type of magnetism will arise. It can give a small ferro component or whatever. Another point is that the oxygen was not in the center, but slightly off. This is charged 2 negative. So this corresponds to something that we have kind of a polarization in this direction, electric field in this direction. So if we would apply electric field, we would induce this time of term in the Hamiltonian. We can think also differently. So suppose that we have some spin configuration where the spins are not parallel to each other, but which have some angle. If this is so, it is possible, and this really happens, that the non-collinear spins will give rise to electric dipole moment. And this is the so-called magnetoelectric coupling. And it is made possible because of spin-orbit interaction. Magnetoelectric coupling, I mean, this is the Katsura-Balatsky-Nagosa mechanism, I think. It had been shown in this, like you have this J1, J2 spin chains where you have different first and second neighbor. Then you will have like a spirally state. It will stabilize the kind of a state that is spiral, where this angle is finite, and then it will give rise to the finite ferroelectric moment in those materials. And these are the so-called multiferroics. When you have coupling of the spin and of different fields, like magnetic field, spins, and electric fields. Since epsilon is small, I'm over the epsilon. I thank you very much for your attention. There are some things that I couldn't tell you, many interesting things, but anyway, I've chosen to go slowly and not to overload you with different things. Thank you very much.
Thanks, Karlo. Would you briefly comment on single ion anisotropies?
We can, why not? Yes, so spin-orbit coupling is, okay, so one of the reasons, spin-orbit coupling can lead to DM interactions, but even more importantly, if you have a higher spin, like spin 1 or spin 3/2, then terms in the Hamiltonian can appear like S1Z square. Such terms can appear. Or if you think about some more complicated systems, like a tetrahedron that is found in the spin ice, then these these anisotropies will choose axes that are pointing from the center of the tetrahedron, and this will be special axes. So it can either give rise to the so-called Ising-like anisotropies, when the interactions are not anymore isotropic, but more like Z component is interacting with the Z component, and we forget about the XY, or maybe more like the X and Y components is more quantum-like. In that case, we can kind of differentiate between the two regimes, Ising, isotropic, Planck-like behavior, and this gives also some more interesting physics in these materials.
Any questions, comments, or thoughts you would like to share? If not now, since we are pretty localized in ICTS as a Mott insulator, and given the heavy rains, there's a large charge gap to go to the city. You're free to catch Karlo on any of the blackboards outside and discuss more, or if you want to discuss more advanced things from here or better understand. Karlo is around for the next 2 weeks. Are there any questions or comments from the online participants? Okay, doesn't seem to be the case. So in which case, let's thank Karlo again for actually giving 2 back-to-back lectures. And we'll go for lunch, and we should reconvene at 2:30. There's a talk by Ronny Thomale on Kagome metals, followed by a talk by Philippe Gegenwart on rare earth Kagome metals again. So it's an exciting metallic session in the afternoon. And so, yeah, let's head for lunch now then.